Okay, let's try sketching 2 sine of this angle equals 1. Now, how do we do it? I recommend you go to desmos.com and just punch this in. We have the first y value, y, or on your TI calculator, y1, is equals to 2 sine 2x minus pi over 3. And when you have an equal sign, that means the other y is equals to 1. So y2 equals 1, or on Desmos you could say y1, y equals, or f of x, g of x equals. So desmos.com will give you the answer. 1. Okay, so here we are on the desmos.com, a great website. And you can see here that we have the two equations here. And what we have is a nice graph. You can zoom in. You can even click on these different lines until you see some nice dots. And you can see where they intersect. They intersect at pi over 4. So x is pi over 4 is the solution. And x is 7 pi over 12 is also another solution. Okay, when you type in the pi into Desmos, you could type in pi. Oh. Okay, so one insight here is, yes, we could rewrite this as two different equations. Another way is to look at the original question and throw everything over to one side. So what we have is, we have 2 sine 2x minus pi over 3, and the 1 goes over, becomes a negative 1. Negative 1 equals 0 because there's nothing left over. So on Desmos, this is like y equals this business here. The y would be set to 0. So here we are back on Desmos. You can see that we typed it in just like we just worked out. And now we're not talking about intersections, now we're talking about intercepts. And so the x-intercepts are 7 pi over 12 and pi over 4. It gives the same result. Okay, now let's try solving this. We're going to solve for x between negative pi and 2 pi. And whenever we see a trig question like this, it's a good idea to look at the angle and treat it as one variable. I'm just going to call it something other than x. I'm going to call it theta. So if I say let theta equals 2x minus pi over 3, my life will be a lot easier. So let's try, this is 2 sine theta equals 1. We're going to divide both sides by 2, and we get sine theta equals 1/2. And now this looks like a regular math question, not so hard. I'm going to pause for a sec. So once we get this kind of question, this is a classic kind of trig question. We know what to do. But I'm just going to pause, and I'm going to analyze this original question in terms of transformations. Okay, so just take a little pause here. I'm hoping that you will get used to this sine problem here. It's pretty okay. I'm going to analyze this original graph in terms of sketching by hand. So right away, I'm going to rewrite it as 2. We have sine, and I'm going to factor. It's a good idea to factor. This x here is a clean freak. We should always factor out the number. Factor out the number even though it's a negative sign. If there was a negative sign here, I'd factor out the negative 1. X is a clean freak. There must be nothing in front of it if we want to think of it as a transformation. So this is going to be 2 bracket. It's going to be something. And this is where you have to kind of build it up. 2 times what is 2x? It's going to be x. And it's going to be 2 times what is negative pi over 3. Okay, so the idea of 2 times negative pi over 6 is negative pi over 3. It takes a bit of mental effort, but please try to concentrate and work that out there. So right now we have an equals 1 over here, but psychologically, if you're going to think of this as a transformation, perhaps we should just think of one graph. So I'm going to throw the 1 over, which becomes a negative 1, and there's nothing left over here. So what does this mean here? Can I even sketch that? All you have to do to sketch this is to multiply the y's by this number here, which is 2. And we multiply the x's by the reciprocal of the b value over here. So we're going to multiply the x's by 1/2. And we're going to shift pi over 6 to the right. If that was a plus sign, it would be pi over 6 to the left. And finally, that number negative 1 all off on the side means down negative 1. And then by sketching this, we can actually find the x-intercepts, which would be the solution of x. Okay, so continuing on with this train of thought here, if we really wanted to sketch it, by knowing how to sketch the regular sine graph, we just apply a series of transformations, doing the stretches and flips first, so this and this first, and the shifts last, and we're going to actually get very good answers visually. So one last good advice in terms of sketching it by hand, if you don't want to just use algebra, which we're about to do, if you have a choice, use algebra. It's just easier. Is to focus on the b value. b is equal to 2. We know that for sine and cosine, not tan, but for sine and cosine, that the period is equal to 2 pi over b. So the period, which we don't know, is going to be 2 pi over this value here, which is 2. So the period is equal to pi. Now, why do I care about that? It's because it's going to help me sketch. So let's just hang on to the fact that sine theta is a half. We'll just come back to that in a bit. So what we have here for sketching this graph, the period is pi. We know how to sketch sine. 1, 2, 3, 4. Sine finishes in 2 pi, or 360 degrees. Sine goes quarter circle up, quarter circle down, down, up, between 1 and negative 1. So we know how to sketch that. But how do we sketch it when the period is pi, not 2 pi? We still go pow, 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 pow for little divisions there. And instead of writing 2 pi, we write the period, which is pi. And here the amplitude here is 2, not 1. So in this case, instead of going 1, we're going to go 2. It's going to go from 2 to negative 2. And already we made some progress by taking care of these two values here. So you can see that sine goes quarter circle up, down, down, up. So already this graph is pretty accurate. The only thing we haven't done is moved it right pi over 6 or down negative 1. Now I'm going to move it down negative 1 just because it's easier. So if we have these nice points locked in, and you can figure out what these points exactly are. This here is half of pi would be pi over 2. Half of pi over 2 would be pi over 4. So this particular point here is pi over 4 comma 2. You can individually transform these points. So for example, if I want to move everything down by 1, literally the graph would look something like this. This goes down by 1. This goes down by 1. So this ends up being negative 3 here. And this point that used to be at pi comma 0 is now at negative 1 as well. So you can see that we actually moved it down by 1. The last challenging part is to shift it pi over 6 to the right. Okay, so the last step is to take this nice graph here, the one that's down, and shift it pi over 6 to the right. How do we do that? We could individually label these points, which would help us. But also another good advice is to divide this graph, these little guiding lines, into appropriate segments. So we have pi over 4 here, but we're interested in shifting pi over 6 to the right. Now that's a bit strange. Now how do we actually work with that? Okay, so if you don't like the idea of subdividing pi over 4 into 3 units, where we have the LCM, the 4 and the 6, LCM is 12. If you don't like that idea, you can literally take these coordinates and just use algebra to simply shift it, add pi over 6, and just work it out that way. But one way of doing it is to take pi over 4 and divide it into 3 parts, which would be pi over 4 divided by 3. You can see there's a dotted line here. It's going to be pi over 12. And so if you say pi over 12 times 2, it's going to be 2 pi over 12, which is the same thing as pi over 6. So we can see here that we're getting these nice equal 3 segments. And the idea of shifting it pi over 6 is going to be about yay wide, which is two of these little jumps. So super roughly, I'm just going to eyeball it here. It's going to be about that much to the right. It's going to be something like that, and I'm just super roughly sketching it. So here we sketched this nice graph in pink, and I would expect that the solutions would be somewhere around here. And let's verify our answer on Desmos. Okay, so on Desmos, we typed in x equals pi, which is roughly here. And you can see that our graph is similar. This here is the one equation, y equals that. We're looking for the zeros. And if you click on the graph settings on Desmos, the little toolbar, you can even click on the x-axis step and type in pi, which means pi. And for certain, you can see the nice pi over 2 divisions. You can even change the steps to be pi over 6. Does that help? You might have to zoom in to see it better. And you can see that this graph is similar to the one we sketched by hand. Okay, so now back to the algebra, the very straightforward math, as straightforward as trig can be. Okay, so what we have here is your classic trig question. Sine, cos, tan, unknown angle is equals to some value. We always go ASTC. All students take calculus. All students take OCATS. All students take chemistry, whatever you can remember. This is just a good little aid to help you remember how to do these fast. So regardless of whether this is 1/2, -1/2, -1, root 2 over 2, root 3 over 2, generally we don't need our calculator when these are very special. But sometimes we do need a calculator, but we still fall upon this ASTC trick. This is positive. Please see that that's positive. Where is sine positive? Sine is positive where you see the same letter S, or in the letter A land, which is all things are positive land. So the question is, sine of what is 1/2? And please memorize that the answer is 30 degrees, or which is equals to pi over 6 radians. Now how do we know that? So please memorize this triangle. This will help you at the beginning of any trig test. This is 30, 60, 90, 1, 2. Trigonometry is easy as 1, 2, root 3. Yes, it's not that easy. So what we have here is sine theta. This is my theta, 30 degrees, is opposite over hypotenuse. This is SOHCAHTOA. So sine 30 is opposite over hypotenuse. This here is a mnemonic. And so we trust that sine 30 is 1/2, and it works here. So we know right away that the candidates for theta is going to be 30 or 150. So I'm going to say theta is equals to 30 degrees or theta is equals to 150. Just always work in the same units as your original question. So right now I'm thinking in degrees. Let's go back to the original question, which is solve x belongs -pi, including the endpoint, to 2 pi. The square bracket means including the endpoint. Rounded bracket means not including. So we're dealing with radians, so I better count in radians. This here is pi over 6, so I'm going to just say this is pi over 6 radians. No units means radians. And I know some students would actually take the effort to go from 150, and they would actually multiply it by pi over 180 to get radians. But this is a bit slower. You may use this if you want. But literally, you can count these pizza slices. This is 30, 1 pizza. This is 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. You can literally just change the numerator that way. 1, 2, 3, 4, 5 pi over 6 is the actual other angle. Theta is equals to 5 pi over 6. So here we did it. We solved 2 different actual theta candidates, and we just have to verify that these answers are within the domain. These answers might not be actually valid. We need to always verify and take one additional step. Now, what does -pi mean? This here is my starting point. On your marks. -pi means go backwards, go clockwise. And we see there's no arms here. The only arms we have is this one here and this one here. So right now, -pi, we did a sweep and there's no answer, so we're fine, we're done. All the way to 2 pi. So 2 pi means go counterclockwise. The normal rotation for angles is this way. 2 pi means 1 full circle. How many intruders do we have? How many burglars? We have alarm goes off here and alarm goes off here. The answer is pi over 6 and 5 pi over 6. So we found the 2 answers, which is all the solutions within the domain. Okay, oh wait, but there's more. Thanks to trig, you have to always be careful. What I just did, because I talked about so many things, is I actually solved for theta. Theta belongs to -pi to 2 pi. But this is great because we did a common mistake. Please don't smoke as I puff my own cigarette. So let's actually go back and recap what we just did here. We just solved for theta. We solved for theta, and we said theta is equals to pi over 6. Great, and we're on the right track. And we said theta is equals to 5 pi over 6. Correct. We did a good job. And these are possible candidates. That's great. However, remember the original question. The original question, we said, let theta equals 2x minus pi over 3. So what we did is we introduced another variable just to help us out. So we're not quite done yet. We're interested in solving for x. We're interested in solving for x belongs to negative pi to 2 pi. And we're not done yet. So I'm going to take this answer here, and I'm just going to plug this business here and replace theta. Let's see what happens. 2x minus pi over 3 is equals to pi over 6. You can see here that this used to be theta, the brackets there. I'm going to say, or I'm going to just go off here. We can say 2x minus pi over 3 is equals to 5 pi over 6. So you can see here now we're starting to find x. We're going to throw the pi over 3 to the right. We have 2x is equals to pi over 6 plus pi over 3, which is the same thing as 2 pi over 6. So 2x is equals to 3 pi over 6, which is equals to pi over 2. There's just a lot of work to be done here. So we have 2x is equals to pi over 2. Divide both sides by 2. We get x equals pi over 4. So there is a possible candidate as a real answer. And another possible candidate we have here is we have 2x equals 5 pi over 6 plus pi over 3, which is the same thing as 2 pi over 6, which is equals to 7 pi over 6. And when I divide by 2, we get x is equals to 7 pi over 12. So we have another candidate here. I'm going to double underline these. Just because we did a lot of work to find these candidates does not mean that it's correct. We always need to check the boundaries, and the boundary here is from negative pi to 2 pi. So what makes this question tricky? Okay, so what makes this question tricky, we just solved. We actually got some 2 correct answers. The domain from being from negative pi to 2 pi. What makes this question tricky is you have to take these 2 answers which we just solved and keep adding and subtracting the period. So if I type in x equals 2 pi, you can see that this blue line here, it introduces new solutions. So if I click on this purple graph here, we have solutions here and here. So these are my 2 original solutions I solved by hand. You take this point here, you add a pi, you get this answer here. And you take this point here, you add pi. So not add pi, but you add the period, and you get this solution here. Similarly, if I type in x equals negative pi, we have another 2 solutions here which we didn't see. And if we click on it, we get the same new answers. Now, how are we supposed to know what these values are? You take our original candidates and you keep adding and subtracting the period. So this first uphill solution is the same as this uphill solution, but just has a distance of 1 full period. Okay, so we just showed Desmos, and we found the first 2 initial circle double underlined solutions. And visually on Desmos, I'm expecting these 2 other solutions as a result of this point here, and I'm expecting 2 other solutions as a result of these points here. And how do we do that? We look at the original question, and we need to basically take this solution and add and subtract the period. This here is adding the period, and this here is subtracting the period. Now, how do we know what the period is again? So we find the period by factoring, and recall the original question was set up like this here. And so I'm just going to factor, which we did already. So I'm just going to do this a bit faster this time. And we know that the period is 2 pi over b, which we solved previously when we sketched it. And so the period is equals to 2 pi over 2 is going to be pi. So that's how we got these values here. We took this and literally added pi, or we subtracted pi. So mentally, you can either factor, or you know what's going to happen to the x. You're literally going to factor out the 2. So psychologically, we don't even have to worry about working out this part here. You kind of know the b value right off the bat. It's going to be 2. Okay, we have this new exciting challenge here. We're going to solve this. We're not going to worry too much about all the details, but one thing we do know graphically, I'm just going to sketch this pretty fast here. Just for transformations psychology, I'm just going to work on just factoring this out here. Now this is already weird. 2/3 times x is 2/3 x, but 2/3 times what is 60? This is a little bit weird already, and I'm going to just leave it as equals 6. Now this is where psychologically I challenge you to add the reciprocal, which is 3/2. Why did I do that? Because 2/3 times 3/2, the reciprocal is 1. So 1 times anything is itself. So I hope you realize that 2/3 times 3/2 times 60 is in fact 60. That itself is a mouthful, but take some time to meditate on that on a mountain. Okay, so I'm just going to rewrite this here. 2 tan. We have 2/3 x plus, now 60 divided by 2 is 30. And so what we have is 30 times 3 is 90. So this is 90 degrees. And this is 6, so I'm just gonna... Okay, so I'm just gonna throw the 6 over. I changed my mind. We're gonna say y is equals to 2. So y equals tan, we have 2/3 x plus 90 minus 6 equals 0. So there's my y value. We're gonna try to find the roots. If we know how to sketch this, this will help us with part B, C, D. So I'm just going to start this first. The solving takes a bit more work. So what does this mean? It means the y's times 2, the x's times the reciprocal of the B value, which is x's times 3/2, or you could say x's times 1.5, a bit wider. And this is 90 degrees to the left, and this is shifted down 6 units. Okay, so we can actually sketch this. I'm just going to get roughly started on the sketch here. So what we have here is the regular tan graph. This is 1, 2, 3, 4. We know that normally it shoots up like that. That's tan. Hopefully you memorize that. But when we're talking about the period for tan is not 2 pi over b. That's a common error. It's actually pi over b. Please remember that. The period for tan is pi over b. The period for sine and cos is 2 pi over b. So we're going to say the period for tan is equals to pi divided by b, which is 2/3. So the period is equals to pi times 3/2, which is going to be 3 pi over 2. So there we go. Normally the period for tan is pi, which takes 1 full cycle like this. That's the period. That's 1 full period. It repeats, and tan repeats. This whole thing repeats again and again. But in this case, it's not the normal pi, but this time it's actually 3 pi over 2 is 1 full period. And here's the asymptote. So this is our new graph. And plus is twice as tall. Normally we had 45 degrees, or pi over 4 being 1, but now this value is going to be 2. This value is literally going to be 2 because the y's are multiplied by 2. Now what is this x-coordinate, just for fun? It's going to be half of this. Half of 3 pi over 2 is 3 pi over 4. And half of that is going to be 3 pi over 8. So we actually know this coordinate exactly. This is incredible. So we're talking in degrees for this example, so I better just rewrite that. So what I have here is this asymptote is 3 pi over 4. And so let's figure what that is. Okay, so going 3 times 180, that's what pi is in degrees, over 4 is 135. So my asymptote here is 135. This here is x equals 135 degrees, but we need to shift it 90 degrees left. So literally my asymptote moves to be 45 degrees. So 135 minus 90 is 45 degrees. And so we have to shift it left, so the first asymptote is actually 45. And now I'm getting a bit of a headache because I'm also expected to shift down 6. So sketching is a little bit more work. But I do know that even though we shift it down by 6, the asymptote remains the same. So what I'm going to say here is Okay, so just to understand and to have a nice sketch, I'm using Desmos, and we see here this is the original graph we're dealing with. And when we predicted that the graph shifted left and then shifted down 6 would look something like this, we were right about the first asymptote, which is 45 degrees. So the first positive equation of the asymptote is x equals 45. And the general equation of the asymptote is going to be the next vertical asymptote. We're going to add one full period to 45. So recall last time we found the period, which is pi over b, is 3 pi over 2, which is the same thing as 270 degrees. What does that mean on Desmos? So on Desmos, it means that if you take this answer of the first asymptote, x equals 45, and we keep adding 270, so 270 plus 45 is 315, x equals 315, that's going to be the next asymptote. And in general, you keep adding 315, you keep adding 270, you're going to keep getting all the vertical asymptotes. So what can we say? The first positive equation of asymptote is x is equal to 45. The general equation is going to be x equals, just pick any correct answer, plus minus the period n. So when we say the period here is 270 degrees, or 270n, when n is 0, we get the correct answer, 45. When n is 1, we get 45 plus 270, which is correct. When n is 2, we get 2 jumps over, 2 periods over. This is the way you find general solutions. And what about the domain and range? Clearly, the range here is all real numbers, and the domain is all real numbers except for those asymptotes. Everything is okay except for where there's no solution, where the asymptotes are. So how do we reflect that? We're going to say y belongs to real numbers. And we're going to say that x, you could say x belongs to real. Oh, by the way, x does not equals to 45 plus minus 270n. So this is the domain is x does not equal to this general solution here, implies that all the other x values are okay. So students always confuse domain range versus equation of asymptotes. Please know when x does not equals to versus when x does equals to.